Hello YouTube! This is another collection of maths problems recorded for the AMSP's Problem Solving Matters course. I've put a link to the AMSP in the description in case you're interested in their maths support. The videos that you're about to see feature Dr Vicky Neale, and there's also a link to her page in the description below. Okay, over to Vicky.
Right, the question defines a function where f of 1 is 1 and f of 2n is f of n and f of 2n plus 1 is the square of f of n minus 2 for positive integers. And what we want to do is find the value of f of 1 plus f of 2 plus dot dot plus f of 100. And my first thought is I don't really know what this function is. It's defined recursively, so it's not going to be very easy to do this calculation. So maybe I'll try to find a few values of f of n for small n and try to get a bit of a feel for what's going on with the function. So if we try to do that, f of 1 is 1, we're told that by definition. F of 2, well 2 is twice 1, so that's the same as f of 1, which is 1. F of 3, so 3 is odd, we're over here. This is going to be the square of f of 1 minus 2, and that gives us minus 1. F of 4, well, 4 is even, we're over here. This is going to be f of 2, which is 1. F of 5 is going to be the square of f of 2 minus 2, which is minus 1. F of 6 is going to be the same as f of 3, so that is minus 1. F of 7 is the square of f of 3 minus 2. And what I've just realised is that I'm doing the same calculation over and over again, because so far all the values we've had for f of n have either been plus 1 or minus 1. Either way, when we square, we get 1 here. We subtract 2, that gives us minus 1. So I think that means that f of an odd number is always going to be minus 1. But the even numbers, so far we've seen 1, but we've also seen minus 1. So there's going to be a little bit more to it. So maybe I'll just work out a few more values to get a feel for this. So f of 8 is the same as f of 4, which gives us 1. F of 9, we just said f of odd numbers gives us minus 1. F of 10, that's the same as f of 5, so that's minus 1. So what happens if I had to work out f of a large even number? What I think I'd do is take that even number and repeatedly divide by 2 and see what happens. And at some point, if I land up with an odd number bigger than 1, then it's going to be minus 1. And that tells me f of my original number. And if not, then I can just keep dividing by 2 and I get down to 1. And so f will be 1 for my very large number. So I think what we discover is that f of k is 1 if k is a power of 2, and minus 1 otherwise. So you can check that if you start with a bunch of values that are all 1 and minus 1, then these rules mean that inductively your values are always going to be 1 and minus 1, and that will prove then that f of any odd number is minus 1. And in terms of other numbers, if we think about writing it as a power of 2 times an odd number, we can do that always. It's either a power of 2 times 1 or it's a power of 2 times an odd number bigger than 1. We can see what's going to happen, and that will explain this rule. So if we try to do our calculation of f of 1 plus f of 2 plus f of 3 plus dot 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 plus f of 100, this is what the question asks us to find, I think that we're going to get plus 1 for each power of 2, minus 1 for all the rest. So the powers of 2, we've got 1, 2, 4, 8, 16, 32, 64. That's 7 of them. So we're going to get 7 with the plus 1s from the powers of 2. And then the other 93 numbers, 100 minus 7, will give us a minus 1. So we get 7 minus 93, which is minus 86. So I think the answer to the multiple choice question is A, minus 86. But actually we can say quite a lot more about the function that we've learnt along the way. The question defines this function, fn of x, and the first thing we're asked to do is to write down f3 of x. So I'm just going to take the expression for fn of x and think about what happens in the case when n is equal to 3. So f3 of x, we're going to get minus 2 all cubed, that's minus 8. When we add 2, so we're going to get minus 6x squared, then plus 6x plus 9. So I think that's all the first part of the question wanted us to do. And now it asks us to find the maximum value of f3 of x. And I think the first thing I'm going to do is ask myself whether this is a reasonable question. Do I believe this function has a maximum? So what does it look like? Well, this function is a quadratic. And because it's got a negative coefficient here, roughly speaking, it's going to have this kind of shape, a parabola, and it will indeed have a maximum. So I believe the question is asking us something reasonable. How are we going to do it? Well, if you know some calculus, you might try differentiating and finding a maximum that way, and that will work out just fine. Because it's a quadratic, I think I'm going to do something a little bit different. I'm going to complete the square, because this is a really nice technique with quadratics, and I like doing it and it makes me happy. But I'm not terribly good at handling quadratics with a negative coefficient at the front. So what I'm going to do is pull out a factor of minus 6 to make my life a bit easier. So I'm going to get x squared in the brackets, and then minus x, so I get plus 6x, and then I think I'm going to need a minus 3 over 2, so that when I multiply by minus 6, I get plus 9. And I feel happier working with this quadratic in the brackets. We say it's monic. The coefficient of the leading term here is 1, so it's a bit nicer to work with. And I'm going to complete the square. So this is minus 6. And then I'm going to do x minus a half all squared, because that's going to give the x squared term, but also it's going to give minus 2 times a half x, so we get the minus x term. The bad news is that it gives us plus a quarter, but we can take care of that. We were aiming for minus 3 over 2, so if I subtract 7 over 4 at this point, we'll end up in the same place. And what's good about this is that we can think about inequalities. So we know that x minus a half all squared is always greater than or equal to 0, because the square of any real number is greater than or equal to 0. So the thing in square brackets is going to be greater than or equal to 7 over 4. So when we multiply by minus 6, remembering to think about the direction of the inequality here, this is going to be less than or equal to 6 times 7 over 4, which is 21 over 2. So that shows that the value of this function is always less than or equal to 21 over 2. To be ultra precise when we answer the question to find the maximum value, we should show that there is a value of x where we achieve 21 over 2, and we know where that value is from completing the square, because we see the only way we're going to get that is when x is a half. So this is attained, meaning f3 of x is equal to 21 over 2 at a half, as f3 of a half is 21 over 2. So our maximum really is 21 over 2. Great, so that seems to be that part of the question dealt with. Then it wants to know for which values of n, fn of x has a maximum value. So I guess I'm thinking about my experience with f3 of x here and going back to the original rather complicated looking function and actually realizing if I think about n as a fixed number here, this is a quadratic in x. It looks kind of scary, but it's a quadratic in x. So what kind of shapes could fn have? Well, it might have a positive coefficient of x squared and be a quadratic in this kind of classic parabola shape. Or it might have a negative coefficient of x squared and be the kind of parabola that we've just been looking at. Or, just being careful, if this coefficient of x squared is 0, then we're going to end up with something that's linear. It's going to look like this kind of shape. And we see that if the leading coefficient is bigger than 0 or equal to 0, we don't get a maximum. But if the leading coefficient, the coefficient of x squared, is negative, then we do have a maximum. So this one has a maximum. So now we have to think about which values of n give us positive and negative coefficients. And it seems to me to make sense to think about whether n is odd or even, because that makes a big difference to what happens with this minus 2 to the n. And if n is even, then that coefficient of x squared, 2 plus minus 2 to the n, that's just equal to 2 plus 2 to the n, because n is even, and that's going to be greater than 0, and that's bad news, we don't have a maximum. Whereas if n is odd, then this coefficient of x squared, 2 plus minus 2 to the n, well, that's 2 minus 2 to the n, which most of the time is going to be less than 0, but could be equal to 0 in the case that n is equal to 1. So we get a negative coefficient if n is bigger than 1, and a 0 coefficient if n is equal to 1. And remember, we didn't want a 0 coefficient because that gives a straight line with no maximum. So what we discover is that fn of x has a maximum value if and only if n is odd and bigger than 1. This question introduces a function f which has the interesting properties that for all x and y, f of x plus y is f of x f of y, and df by dx is f of x, and f of x is strictly positive. And we define a to be f of 1, and the question slightly cryptically tells us that we can't use the exponential function. I guess that's because secretly we know that the exponential function satisfies these properties, but it's really important that we only refer to these properties, not any other intuition we might have about the exponential function or anything like that. So our first job is to show that f of 0 is equal to 1, and my thinking here is that we should look at the top one, because we know that f of 0 I can write as f of 0 plus 0, which is f of 0 times f of 0 by this given property. And we know that f of 0 is strictly positive by the third property, so it's not equal to 0. So we can cancel f of 0 from both sides, and that gives us that f of 0 is equal to 1. So that falls out pretty nicely. So far, so good. The next part asks us to think about the integral from 0 to 1 of f of x dx. And at first sight, sort of think, well, how can I possibly answer this? Because I don't even really know what f is to be able to integrate it. But one thing we know about f is that it is equal to its own derivative. And I'm thinking that's going to be pretty useful because that's going to interact nicely with the integration. So this is the integral from 0 to 1 of the derivative of f with respect to x, integrated with respect to x. And there's this fantastic result called the fundamental theorem of calculus, which relates integration and differentiation. And this tells us that this is just f of x evaluated between the limits 0 and 1. So that's f of 1 minus f of 0. And we know that f of 1 is a, because that's how we defined a. And we know that f of 0 is equal to 1 because we just showed that. And that gives us what we wanted in this part of the question. So now I'm going to move on to part 3, which asks us to think about using the trapezium rule with n steps to estimate this integral. And I have a vague idea there's a formula for the trapezium rule, which I honestly can't remember. So I should just figure this out from first principles, because I think I can just draw some pictures of trapezia. I think it'll be fine. So here are my axes. Here's 0, here's 1. This is the area we're interested in. And we know that f of 0 is 1, so we kind of start here somewhere. And because f is always strictly positive, and the derivative is equal to f, that means the derivative is always strictly positive, and so our function is increasing. So who knows what it does? It might kind of increase in some kind of complicated way, but let's kind of draw something. I mean, secretly we sort of know what it looks like. And in particular, we know that f of 1 will be bigger than f of 0, so a is bigger than 1 up here. So what does the trapezium rule do? Let me find a different coloured pen. The trapezium rule, we say, well, we're not quite sure how to do this, so let's chop this up into regions of width 1 over n. So this is 2 over n, and 3 over n, and so on. And then instead of trying to do the area under the curve, we do the area under these trapezia. I haven't drawn this terribly brilliantly, but hopefully that's kind of what the trapezium rule is about. And while I can't remember a formula for the trapezium rule, I can remember how to work out the area of a trapezium, because we average the lengths of these two parallel sides, and then we multiply by the width. So we sort of make it like a rectangle with the average height going on there. So if we think about the trapezium, well, actually, I've just noticed the question says we're going to let B be f of 1 over n. And I think that's quite interesting, because then f of 2 over n is f of 1 over n times f of 1 over n, using the first property, so that's b squared. And more generally, I think we're going to see that f of I over n is b to the I, by using the first property over and over again. We're just adding 1 over n each time. And also, I guess f of n over n is b to the n, but we know that this is f of 1, which is a, so we've got a relationship between a and b, which I think might be useful. So if we think about the area of the trapezium being slightly informal from I over n to I plus 1 over n, I just mean one of these single trapezia. Hopefully you see what I mean there. How am I going to work that out? Well, I do a half, and then I need to average these heights. So f of I over n plus f of I plus 1 over n, and then the 2 out the front does the averaging, and then I multiply by the width, which is 1 over n. And we've just said that we can think of this in terms of b, so that's going to be 1 over 2n, and then we're going to get b to the I times 1 plus b, using that relationship. So by the trapezium rule, I say that very grandly, I mean, I'm just using this area of this trapezium and adding them up lots. We're going to add for each of these, so I is going to go from 0 to n minus 1. So this is going to give us the sum from I is 0 to n minus 1 of 1 over 2n b to the I 1 plus b. I'm going to pull out 1 plus b over 2 to the n at the front, because that's constant. And then this is the sum from I is 0 to n minus 1 b to the I. And now I'm doing a little happy dance, because this is a geometric series, and I know about the sum of this. So we're going to get 1 plus b over 2n. And then the sum of this, we're going to get b to the n minus 1 over b minus 1, because we've got n terms here. We're going from 0 to n minus 1. And I've just remembered that b to the n is a, because we said that earlier on. And I've also just looked back at the question to remind myself what it says. So I'm going to write this as 1 over 2n times b plus 1 over b minus 1. I've got these terms here. And then this b to the n minus 1 has just become a minus 1, which tragically has fallen off the edge of the page. Let's see whether I can fix that for you. There we go. That was slick and seamless, wasn't it? But we got the formula in the question, and it didn't matter that I couldn't remember the trapezium rule, so that's all good. I knew the idea, which is the important thing. And now let's hop over and have a look at part 4. So we're now allowed to assume that in is greater than or equal to I for all n. And we have to prove this inequality, which intriguingly doesn't involve b. So that's something to think about. So my plan is just to kind of rewrite this. So in we've just established is 1 over 2n times b plus 1 over b minus 1 times a minus 1, sorry. And that, we're told, is greater than or equal to I, which in a previous part we discovered was a minus 1. And what I really want to do is divide through by a minus 1. And I have to have a pause for a moment, because I've got an inequality here. So not only must I not divide by 0, but I have to think about whether I'm dividing by something positive or negative. But I think that a, which is f of 1, is strictly bigger than f of 0, which is 1. From the assumptions in the question, we know that our function is strictly increasing, so we can divide through to get the 1 over 2n, b plus 1 over b minus 1 is greater than or equal to 1. At this point, I'm not feeling massively encouraged because we were supposed to prove an inequality about a and this doesn't involve a, but I do remember somewhere along the way that we knew that b was related to a, so maybe it will be okay. My plan is to rearrange this to try to get b by itself. So talk amongst yourselves, I'm just going to do algebra for a bit. So I think this tells us that, let's see, b plus 1 is greater than or equal to 2n b minus 1. So b times 2n minus 1, bringing all the b's over here, is going to be less than or equal to 2n plus 1. So b, I'm carefully making sure that each time I multiply, I'm dealing with positive quantities, but it's all good. So b is going to be less than or equal to 2n plus 1 over 2n minus 1, which looks a little bit like the thing in the question, but not quite. But if I rewrite that, that's 2n minus 1 plus 2 over 2n minus 1, which is 1 plus 2 over 2n minus 1. I'm being steered by what the question is aiming for here, right? So this shows that b to the n is less than or equal to 1 plus 2 over 2n minus 1 to the n. And the reason I've done that is that b to the n is equal to a. So I'll just squeeze in the bottom here. A is less than or equal to this. Maybe I'll just write here b to the n is equal to a to remind you where that came from. And so we've proved this intriguing inequality, which secretly we know what a is. Secretly we think about a using the exponential function. So in fact we just proved an interesting inequality involving the quantity e. But don't tell anybody I said that.